In chapter 29, we're going to use the quantum physics that we learned in the previous chapter to see if we can't learn something about the structure of the atom. So we probably, most of us, have this model of the atom in our mind. We've got the nucleus in the middle and then the electrons winging around the outside. And we probably encountered this model for the first time in grade school sometime, right? It's pretty well established. But nobody's ever seen an atom, right? So how do we know that that's what the structure of the atom is? Right? The atom is so much smaller than the wavelength of light. We can't use light to look at it. We can't use an electron microscope to look at it because it's even smaller than the wavelengths we can produce with electrons in an electron microscope. So why do we believe this atomic model? It's been very successful. But why do we believe it? And how did scientists develop this model? Well, that's what we're going to talk about in this chapter. Here we see a picture. This is about the best pictures we can get of atoms. This is the so-called atom corral, is what they call this. And it's not a picture in a traditional sense like a photograph, right? This is not a photograph. We talked a little bit about how this is made in the previous chapter. This was made with a scanning, tunneling electron microscope. In a sense, this is a map of the probability of finding an electron at each of these locations. And so we see that electrons are much more likely to be found here and here and here, and those are the locations of the atoms that form this ring. Interestingly, this center spot here, that is not an atom. There's not an atom in the center of this corral. This is actually the electron waves adding constructively in the center. So we're more likely to find an electron here in the center than we are just a little bit farther over here. That's a little bit surprising. Again, this is evidence of the constructive interference of the matter waves of the electrons in these atoms in this ring. So that's pretty interesting. Okay, so we cannot see an atom. Then how do we know the structure? How do we know the shape of the atom, the structure of the atom? Well, one of the most powerful tools for investigating not only the structure of an atom, but also the makeup of some object is spectroscopy. And so spectroscopy is a technique that was invented in the 1800s, and this allows us not only to probe the structure of the atom, but also to figure out what, say, a distant star is made out of. Every now and again, there'll be some news headline. There was one a few months ago, I suppose, and it said, new exoplanet discovered, and its atmosphere has a bunch of water in it. How do they know that there's water in some planet that is light years away? Certainly nobody went there and was like, oh, here's some water. No, it turns out spectroscopy is how they knew that. So spectroscopy is this powerful, powerful technique. And the way it works is you have some light source. Maybe it's a distant star, but maybe it's just a little gas discharge tube that we have here on Earth even, right? And you send it through some lens, and the only point of the lens is to focus that light through this slit. So we focus the light through the slit, and you hit a diffraction grating. This diffraction grating separates the colors into their constituent wavelengths. It works just like a prism, right? Recall that when we did diffraction grating with light, recall that when we did that, we found that the angle that the light was diffracted to depended upon the wavelength. So we see that red light, blue light, infrared, ultraviolet will all get diffracted at different angles. Thus, just like a prism, a diffraction grating spreads light out into its constituent colors. And we can see that just a little bit. I'll take us on a little journey here. Here I am looking at a light bulb in my basement, and I'm using these rainbow glasses. These are pretty sweet. If I look around, I see rainbows everywhere. So this is what I need in my life right now. I used to wear those all the time. But if I hold these up to the camera, and maybe you can see a little bit. Oh, if I get the angle just right, then we can see that rainbow produced from this light bulb. And again, this is this diffraction grating breaking white light up into its constituent colors. And we see a pretty continuous spectrum here. It kind of smoothly goes from purple to green to red. All right, taking you back to my office. So that light bulb gave us this nice continuous spectrum, much like we see here. But we'd see something different if we were looking at just a gas that was excited. And you've actually seen this before. The classic neon open sign red. What that is it's a glass tube filled with a neon gas, and that neon gas has been excited. It's been energized, and it releases its energy in the form of photons. And as it does that, it produces this nice reddish, yellowish, orangish kind of color. So you've seen that a lot, but different gases in tubes can produce different colors. Here's krypton, argon, helium. These are some noble gases, but you know what? It doesn't have to be a noble gas. You could use mercury vapor, is pretty common. Any gas, really, if you put it in a tube and you excite it with electricity, it will glow. Every gas glows with a slightly different color. And here we see this picture of a city scene, and boy, you just see all the colors, a whole rainbow of colors here. Right? And a lot of these are gas discharge tubes. Probably not all of them, but a lot of these colors are produced by gas discharge tubes. And so when we see this lovely neon color, this reddish color here, well, it turns out that it's actually a number of different wavelengths that all add together to give this effect. If we were to break neon into its constituent colors by running it through a spectrometer, then what we would see is that it's actually a whole bunch of different colors. And if you put them all together, you get that nice red color. Different gases have different patterns. Mercury has this pattern, neon has this pattern, hydrogen has this pattern. It's like a fingerprint. And using this idea of a fingerprint, you can identify what a gas is. In fact, helium was discovered in the 1800s on the sun before it was discovered on Earth, because folks looking with their spectroscopes at the sun, don't try that at home, saw a fingerprint for a gas that they had never seen on Earth. And scientists said, hey, I've never seen this on Earth. It must be a new gas. And I've only seen it on the sun. Let's call it helium after Helios, which means the sun. Okay, so a hot object releases this continuous spectrum. Here's a hot object. It releases a continuous spectrum. We've actually seen this before. Remember Wien's law? Wien's law told us that the peak wavelength depends upon the temperature. And not only does the peak wavelength depend on the temperature, but the amount of energy also depends on the temperature. Now, and the wave. But a hot object emits all of the colors, right? It emits a hot solid object, emits all of the colors from the lowest wavelength all the way up to the highest wavelength it emits in a continuous spectrum. But remember, we didn't see that with those gas discharge tubes, where we're just looking at a single kind of atom. And the other thing about those gas discharge tubes is that the atoms are dilute enough, they're at a low enough pressure, that the atoms are really not affecting each other too much. They all kind of have their own space. So in a way, what you're seeing when you see this light from a neon discharge tube, you're seeing the light from a single neon atom. Now, there's a whole bunch, and so it adds up to make a nice bright light. But what I'm saying is that those atoms are not interacting with each other. You're not seeing the light that would be produced by helium atoms, or neon atoms, interacting with each other. You're seeing light from neon atoms that are sort of isolated because that gas is so dilute. Now, what we can do is we can reverse this situation. Instead of having the light created by our dilute gas, instead we can take white light, and remember that white light is all of the colors put together. We can take all of the colors put together and we can send it through some sort of a cell that is filled with that gas. And now, instead of seeing what colors the gas produces when it's excited, now we see what colors that gas absorbs when we pass light through it. So I pass this light through this gas cell, and some of the colors are absorbed. We call that the absorption spectrum. And notice that the absorption spectrum and the emission spectrum, they line up with one very big difference. Not all of the lines that are in the emission spectrum also appear in the absorption spectrum. In fact, there's a whole bunch of lines in the emission spectrum that don't appear in the absorption spectrum, whereas all of the lines in the absorption spectrum are also in the emission spectrum. Okay, so scientists learned all of this in the 1800s. How can we use this to help us understand the structure of the atom? Well, one of the first clues was developed by a man named Balmer. And this was, again, we're still in the 1800s. And Balmer was actually not really a professional scientist. He was actually a science teacher. And he was looking at this puzzling hydrogen spectrum, which was well known at the time, but a completely unsolved puzzle. And he noticed that this formula right here would produce the wavelengths of the visible spectrum of hydrogen. So there's 4 visible lines in the spectrum of hydrogen: 410 nanometers, 434 nanometers, 486 nanometers, and 465 nanometers. And so what Balmer figured out is that applying this formula, he could come up with these lines. That's pretty interesting. And again, he came up with it empirically. He just noticed that it fit. He didn't really know why it fit, or he didn't even really have a good theory as to why it fit, but he just noticed that it did. And so in order to produce this spectrum, he noticed that if you plug in 2 here, and then something bigger than 2 here, you'll get these 4 lines. So for example, if we were to plug in this, then we would get 656 nanometers. And that is the longest wavelength in what we call the Balmer series. If we were to plug in 4 for here, we would get the next line. Plug in 5, we'd get the next line. Plug in 6, we'd get the next line. So Balmer noticed this. And again, he didn't really know why this worked, but it did work. It turns out if we plug in not 2 here, but 1 or 3, then we can get another set of spectral lines. If we plug in 2 here, if we plug in 1 here or 3 here, then we'll get a whole nother set of spectral lines. Now, these are the only 4 lines in the visible spectrum, but hydrogen has a lot of spectral lines that are outside of the visible spectrum, in the infrared or the ultraviolet. And so plugging in a number other than 2 here can help us to find those other spectral lines. But, of course, in the 1800s, these 4 were the only ones that folks could observe. And, yeah, so that's the truth. And so, for historical reasons, because this was one of the very first sort of, again, clues as to the structure of the atom, these all have fancy names. So if we plug in m equals 1 here, then this is called the Lyman series. If we plug in m equals 2, it's the Balmer series, which gives us the visible spectrum. And if we plug in m equals 3, it's known as the Paschen series. You don't need to memorize those names, but that's what they're called.